Yes, children, in continuation with the previous topic of chapter 2, that is structure of atom. So I was teaching about structure of atom, which is nothing but the second chapter. Right. In this, I was teaching about the nodes, NODES. Nodes or nodal surfaces or nodal regions. Node means the region where the chances of finding electron is zero. We cannot find the electron. So that part is said to be node. And these nodal surfaces are there in the orbitals. If you take any orbital, that orbital definitely will have nodal surfaces. And number of nodes can be calculated by the formula n minus 1. First let me write once again. Node means the region where chances of finding electrons is zero. Means in that region electron doesn't exist. Next, number of nodes can be calculated by the formula n minus 1. This is the formula used to calculate number of nodal surfaces or nodes. If you take first shell, that is 1s, if you take s orbital of first shell, that means 1s. In that case, s orbital of first shell has no nodes. So first shell means n is equal to 1. Right? So number of nodes is equal to n minus 1. And that is equal to 1 minus 1, that is 0. So that way 1s orbital doesn't have any node. This is one example. Now we'll move to s orbital or second shell. Second shell is 2s. S orbital is there in second shell. N is equal to 2. So 2s. It has how many nodes? Let us see. Has one node. Now we will verify with the formula. That is n is equal to 2. Therefore, number of nodes, that is 2 minus 1. Formula is n minus 1 and that is equal to 2 minus 1 is equal to 1 node. So 2s has only one node. Now let us see how is this diagrammatically shown. If you take 1s orbital, it looks like this. This is 1s orbital with 0 nodes. When there is no node or nodal surface or nodal region. If I move to second s orbital, this is 2s orbital. In this 2s orbital, this region means the area which is lying around the small circle is said to be the node. Right, where chances of finding electron is 0. So in that way, the number of nodal surfaces are calculated. If we move to 3s, then there 3 is principal quantum number. So in n minus 1 formula, if we substitute n value which is equal to 3, then we will get 2. That means 3s has 2 nodal surfaces. That's about calculation of nodal surfaces. Now we'll move to important concepts. They are ground state and excited state. Now let us see what is meant by ground state. This refers to a particular state where the energy possessed by the electrons is minimum. Whenever energy possessed by the electrons is minimum, stability of those electrons are said to be maximum. So in ground state, electrons possess minimum amount of energy, which is accountable for maximum stability. Now if we move to excited state, in excited state electrons will have maximum energy and the stability is minimum. How can electrons get extra energy? Each electron has particular amount of energy in ground state. If the amount of energy possessed by the electron is increased, means when it becomes maximum, then that electron is said to be unstable, and immediately that electron will take jump to next subshell of the same main shell, or it may take jump to the next shell. So here jump may occur from one shell to the other shell, means from one principal quantum number to the other principal quantum number, point number 1. Point number 2, that electron may take jump with the shell from one subshell to the next higher subshell. So in any way, jump of the electron can take place once that electron is excited. So here, excited state refers to the state wherein electrons possess maximum energy that is accountable for minimum stability. Right. It can be understood with the help of diagram in this way. Imagine s orbital which is there in first shell, 1s. After that we have 2s, 2p. After that 3s, 3p. Next comes 3p and 3d. But 3d. Next 4s, 4p and so on. We'll move up to 3d and let us see. Here as we move from 1s to 2s, 2p, 3s, 3p, etc., energy is possessed by the orbitals which are there in concerned principal quantum number also increases as we move up. In ground state, electrons, imagine they are there in 1s, 2s, 2p, 3s, 3p, etc. The energy possessed by 2s is almost similar to 2p. Energy possessed by 2s means the electrons present in 2s, how much energy they have. That is nothing but the energy possessed by 2s according to Broglie's rule. So also 2p. This is in ground state. Now if we move to excited state, 1s orbital, next 2s, 2p, 3s, 3p, in that way it is. So here energy values, imagine are taken on this axis. This is the case of excited state. Imagine electron is there in 2s, right? Let me show that 2s, we are from 2s. Yeah. If we give small amount of energy to such atom wherein electron is there in 1s, imagine it is hydrogen atom. Its atomic number is 1, so electronic configuration is 1s1. Now, if I give small amount of energy to 1s, what happens is the electron present in 1s will take jump to 2s. Right? The energy possessed by 1s electron is this much. And once the electron takes jump from 1s to 2s, the energy possessed by 2s means the electron which is there in the 2s will become this much. Means energy is increased. Again, if we give energy, the electron present in 2s can take jump to 2p or it can take jump to 3s, depending on how much energy we are going to give. So, electron may take jump from 2s to 2p. Then also the energy possessed by the 2p electron will be this much from the origin. Means, as we go on give energy to the electron present in a particular subshell of the main shell, that electron will take jump from its shell to the next shell or from its shell to the next subshell. In that way, the net energy possessed by the electron in concerned subshell of the main shell will become maximum. Then that state is said to be excited state. So in excited state, the energy possessed by the electron becomes maximum, which is accountable for minimum stability of the electron. That's about excited state and the ground state of electron. Fine. Now we will see how to calculate the number of electrons present in each shell, and then we will go ahead with the rule, that is Broglie's rule, to find out the energy possessed by the orbitals which are located in the subshells. In turn, the subshells located in the main shell. Now let us see calculation of electrons present in the main shell. Calculation of electrons present in the main shell. Here main shell means n. That means principal quantum number. Right. So number of electrons present in any principal quantum number or main shell is calculated. It is calculated by the formula 2n square. It is calculated by the formula 2n square, where n is equal to shell number, main shell number or orbit number or main energy level number or principal quantum number value. All these means same. Now let us see some examples. Example 1. Number of electrons in first shell means n is equal to 1 is calculated in this way. This value 1 is substituted in n of 2n square formula. So 2 into 1 into 1 square. N is equal to 1. It is 4 electrons. Next, n is equal to 2. 2 into 2. 1s2, 2s2, 2p6. First shell 2 electrons, next 8 electrons. Next, n is equal to 3. When n is equal to 2, the number of electrons accommodated will be 8 electrons. So it is obtained in this way. N value is substituted. Right. Next, when it is equal to 3, then it is 18 electrons. In that way it is substituted. If n value is equal to 1, n square 1 into 1, 1 into 2, 2 electrons can be accommodated when shell number n is equal to 1. If n is equal to 4, then the electrons number is calculated in this way. N value is 4. 4 into 4 16, 16 into 2 32. So 32 electrons can be accommodated in 4th shell or 4th main shell. In that way, the number of electrons that can be accommodated in the case of different principal quantum numbers can be calculated. So this is example 2, number of electrons in n is equal to 3. Example 3, number of electrons and n is equal to 1. In the last example, number of electrons and n is equal to 4. In this way it is calculated. That's about calculation part of number of electrons in the case of different main shells. Let us see the energy possessed by the subshells which belong to different main shells with the help of Broglie's rule. So this Broglie's rule speaks about the energy possessed by different subshells of the main shell. Now let us see examples. This is also known as N plus L formula. N plus L. In this, N represents principal quantum number, L represents azimuthal quantum number. So in N plus L formula, N is equal to principal quantum number is also called shell number or shell value or orbit number or orbit value. Next, L stands for azimuthal quantum number. This refers to subshell number. That means electrons are there in the subshells and these subshells are located in the main shell. Now let us see example 2s and 2p. Together only one example. In this let us see the energies possessed by 2s and 2p and then we will compare which one has less energy than the other. And always keep in your mind S value is 0, P value 1, D value 2 and F value is 3. This should be there in the mind. Now 2s means 2 refers to the shell number and value of S subshell is 0. It is written here. So 2s means 2 plus 0 is equal to 2. Simply it's a number, doesn't have any unit. Now, if we move to 2p, 2 plus p value is shown here. It is equal to 1. So 2 plus 1 is equal to 3. So 2s has the value 2, 2p has the energy value 3. So in that way, 2s energy is less than 2p. That is the rule. Whenever a particular subshell present in a particular main shell has less energy than the other, into that electron will enters first. Means always enters into the orbitals of different subshells present in the main shells in the order of what do you call increase in the energy. So one which has minimum energy will be filled first with the electron. Means here out of 2s and 2p, if you take electron will enter into 2s first, thereafter 2p. Now let us see example 2, 3d and 4s. Here 3d and 4s together will constitute only one example. According to Broglie's rule now, 3d is equal to 3 plus d value is shown here, it is equal to 2. So 3 plus 2 is equal to 5. If we move to 4s, principal quantum number, that means n value of that Broglie's rule, this n is equal to 4 plus L is nothing but S whose value is equal to 0. It is equal to 4. Now out of these two, when we compare, 4s has the energy value equal to 4 and 3d has the energy value equal to 5. So in that way the energy possessed by 4s is less than 3d. So 4s energy is less than 3d. That means electron will enter into 4s. Once it is filled, then the electron will enter into 3d. That is the synopsis of this rule. Now we will take one more example where in energy values are same. In that case, what should be taken into account to decide the entry of the electron? Let us see that example also. That is, say, example 3. In this example 3, we are going to take 4p and 3d. 4p and 3d. According to Barber's rule, 4p energy value is 4 plus p value is shown here, that is 1. So it is 5. Now 3d means 3 plus d value is 2. So it is 5. Now 4s and 3d both have same energy values. In that case, into which subshell of the main shell electron should enter? That is the point. When energy values are same, right? In that case, electron will enter into that subshell whose principal quantum number is less than the other. So electron will enter into 3d because principal quantum number of 3d is 3, which is less than the principal quantum number of 4p, which is equal to 4, right? So entry of electron will occur in that what you call subshell whose principal quantum number is less than the other. That means electron will enter into 3d. That means electron will enter into 3d. This is the synopsis, and this is what you call the unique example where energy values are same. Now we will move to an important topic which is there in class 12th also, that is filling up of orbitals with electrons. Always electrons will enter into those orbitals which are associated with small amount of energy first. Thereafter, electrons will enter into other orbitals which are associated with more energy. And in this we have Aufbau principle. So according to Aufbau principle, electrons will enter into the orbitals which are associated with small energy first. Thereafter, electrons will enter into other orbitals which are associated with large amount of energy. And here we have memory 8. That memory 8 you need to remember so that you can write electronic configuration correct without any error. First, what you need to do is show 7 circles. Seven vertical structures, circles. 3, 4, 5, 6, 7. And it can be labeled as 1s, 2s, 3s, 4s, 5s, 6s, 7s. After that, 1, 2, 3, 4, 5. 2p, 3p, 4p, 5p, 6p. Next, 1, 2, 3, 4. 4 circles, wherein you need to write 3D, 4D, 5D, 6D. Next 2 circles, they are 4, 3D, 4F, 5F. Now let us see the entry of the electrons. First you show the solid lines. Now in between the orbitals, circles, we show the dotted lines. These are the clues to remember to draw the diagram without any error. Now, you need to join in this way. The solid line, you need to join this way, and the dotted line this way. This is the memory aid that is useful for writing electronic configuration. So electronic configuration means distribution of electrons in the orbitals of different subshells. So first electron will enter into 1s. Once it is filled, it will enter into 2s. Once 2s is filled, electrons will enter into 2p. Once it is filled, electrons will enter into 3s. After 3s, 3p. After 3p, 4s according to Broglie'S rule. Once 4s is filled, electrons will enter into 3d. After that, 4p. Once 4p is filled, electrons will enter into 4s. In that way, entry of electrons will take place. Now, let us see example for electronic configuration. Electronic configuration is nothing but distribution of electrons. According to Aufbau principle, electrons will enter into orbitals of concerned subshells which are associated with small amount of energy first. So here we will take sodium, atomic number is 11. So electronic configuration is 1s2, 2s2, 2p. In 2p we have 3 orbitals. So that can be designated by 2px, 2py, 2pz. So 4 electrons over 5, 6, 7, 8, 9, 10 over. But we have 11 electrons. So 11th electron will enter into 3s. It becomes 3s1. And this part 2px to 2pz can be replaced by 2p6. In that way also it can be written. Right. Now let us see another example, that is argon, whose atomic number is 18 and electronic configuration is 1s2, 2s2, 2p6, 10 electrons over. So So 18 minus 10, still 8 electrons. So 3s2, 3p6. This 3p6, if we want, we can expand it to 3px2, 3py2, 3pz2, or directly you can write 3p6. So that's how you need to write the electronic configuration. To write the electronic configuration without any error, this memory 8 you need to remember. That's about Aufbau principle and electronic configuration of some elements like sodium, argon. You can write electronic configuration for any element till 118th element. They have 118 elements right now in the periodic table. So you can write electronic configuration till 118 elements. Now let us see Pauli's exclusion principle. According to Pauli, the scientist, no subshell, no orbital of any subshell can get paired electron till all the orbitals of that subshell are filled with 1 electron each. If you take P subshell, it has 3 orbitals. Once these 3 orbitals should be filled with 1 electron each. Thereafter, pairing of the electron will begin from the first orbital. So, pairing of electron will not occur until all the available orbitals are filled with 1 electron each. This is the principle. With the help of example, it can be understood in this way. If we take nitrogen, whose atomic number is 7, we can write electronic configuration keeping Aufbau principle and Pauli's exclusion principle in this way. 1s2, 2s2, so 7 minus 4, 3 electrons are there. Now their entry is like this. 1s2, 2s2, 2px, py, pz. Now each orbital gets filled with 1 electron each. Now total number of electrons are 7. This is electronic configuration of nitrogen. If we move to oxygen, whose atomic number is 8. Here pairing is going to take place in 2px in the case of oxygen. Let us see how it is going to take place. 1s2, 2s2, 2px, py, pz. Px, py, pz are the 3 different orbitals. So they are filled with 1 electron each. If we count total number of electrons, 4, 5, 6, 7. Now 8th electron gets paired with the electron of 2px. Now if we move to fluorine, whose atomic number is 9, electronic configuration 1s2, 2s2, 2px, py, pz. So 7 electrons. 8th electron will join with 2px, 9th electron will join with 2py. Now total number of electrons are 4 plus 5, 9, which is nothing but atomic number of fluorine. So in this way, the electronic configuration of the atoms of different elements are written, keeping Pauli's exclusion principle in the mind. So once again, according to Pauli, pairing of electrons in any orbital of the subshell will not take place until all the orbitals of that subshell are filled with one electron each. Thank you, children. Welcome back to online classes once again. Now let us see condenser electronic configuration. What is meant by condenser electronic configuration? Condenser means making small. Whenever we write electronic configuration for any element, that electronic configuration can be made short by choosing the nearest noble gas element. Now, which elements are called noble gas elements? Those elements whose outermost shell is completely filled, example helium, or completely filled with 8 electrons, that is octet, example neon onwards. Argon, neon, krypton, xenon, and so on. Now let us see one example for condenser electronic configuration. Electronic configuration of lithium will take first. Atomic number is 3, so we write electronic configuration 1s2, 2s1. This is electronic configuration of lithium. Now, condenser electronic configuration of lithium. Here the nearest noble gas element of lithium is helium. So we write He in square bracket like this and then 2s1. Here helium atomic number is 2, so it will have 2 electrons. And 2s1 we have 1 electron. So 2 plus 1, 3. The electrons present in this square bracket of helium are called core electrons. And the electrons present in 2s1 means outermost electrons are said to be the valence electrons. Right. Next we will see example 2, that is electronic configuration of aluminium. Its atomic number is 13, so its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p1, 4, 6, 10 plus 2, 12 plus 1, 13. Now let us see condenser electronic configuration of aluminium. Nearest noble gas element of aluminium is neon, whose atomic number is 10. Means this part we are going to replace. In the case of lithium, we replace 1s2 with helium. And in the case of aluminium, we are going to replace this part with neon. Neon has 10 electrons. After neon, we have 3s2, 3p1, part of electronic configuration. So 3s2, 3p1. This is called condenser electronic configuration. As usual, the electrons present are associated with the neon, which is shown in the square bracket, is said to be core electrons. And these electrons are said to be the outermost electrons. So that's about the condenser electronic configuration. Next, elements and types. we have three different types of elements. They are: number one, halogens; number two, noble gas; elements; and number three, highly reactive elements, that is alkali metals or elements. Halogens means those elements which are able to form salts, and these elements contain one electron less, thereby to get stability, means to get 8 electrons arrangement in the outermost shell. These halogens have to gain one electron. Therefore, halogens are highly electronegative. And always tends to gain electron. Next, noble gas elements. Those elements whose outermost shell is completely filled are called noble gas elements, and the name noble is given to these gaseous elements because it is their ability not to react with other elements. They don't react because their outermost shell is completely filled, so they don't require electrons to gain, or they don't require electrons to be given. So noble gas elements are highly stable elements, and their outermost shells are filled completely. Example, helium, 1s is completely filled. In rest of the elements of noble gas group, in all those elements, octet is achieved, means 8 electrons arrangement is achieved. Now come to alkali elements. These elements contain one extra electron in their outermost shell. Therefore, these elements tend to get stability by losing that electron. That is why these elements are highly unstable. Right. Next, one more concept associated sentence is there in the NCERT book, that is short-lived elements. Means life of those elements is very, very short. So short-lived elements means their life is very short, and these elements will come immediately after uranium. So whichever elements are there after uranium in the periodic table are said to be short-lived elements. Next then we will move to the relationship between electronic configuration and the stability of the elements. Electronic configuration means it is known to us. It is nothing but distribution of electrons. So before going to see the stability, in each orbital how many electrons are accommodated, and in each subshell how many electrons are accommodated. Let us see this, thereafter we will move to the relationship between electronic configuration and stability. So about the accommodation power of the electrons in the orbitals, there is a rule, and name of that rule is Hund's rule of maximum multiplicity. Hund's rule of maximum multiplicity. This refers to the maximum electron accommodation capacity of the orbital. One point. And this rule also tells that for any two electrons, all the four quantum numbers cannot be same. First three quantum numbers, principal quantum number, azimuthal quantum number and magnetic quantum number. These three quantum numbers can be same, but always the fourth quantum number for those two electrons of the same orbital will remain different, because out of those two electrons, one electron can have clockwise spin and the other electron can have anti-clockwise spin. So in that way, fourth quantum number will be always different for the paired electrons of the same orbital. So according to Hund's rule of maximum multiplicity, no two electrons can have all the four quantum numbers same. It means if the first three quantum numbers, namely N, L, ML, are same, it means if the first three quantum numbers N, L, ML are same, but the fourth quantum number will be always different. That is the summary of Hund's rule of maximum multiplicity. It also tells that any orbital, if you take any orbital of the subshell, its capacity will be only 2 electrons. Electron accommodation capacity of any electron, any orbital is 2. Means it cannot accommodate more than 2 electrons, but it can be less than 2. Next we will move to electronic configuration and stability of atoms of the elements. That is the relationship between electronic configuration and stability. This is the topic. The important point of this topic is whenever the subshell is completely filled, or complete shell if you take second shell, third shell, etc. Whenever it is completely filled or exactly half filled, then it is said to be stable. So half filled and completely filled shells with electrons are stable. Now let us see example for this. Example 1. Chromium atomic number is 24. Its electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 10, 20, 12, 18, 20. 4 more electrons are there. 3d, 4 we write like this. Now, if we take the outermost shell, 3d, it is neither half-filled nor fully filled. That means chromium metal should be unstable, but chromium metal is stable. To account for its stability, what we are going to do is, out of 2 electrons of 4s2, 1 electron will shift to 3d. Then 3d will become exactly half-filled, so also 4s. Right? The electronic configuration will become 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d, 5. Now this is exactly half-filled, so chromium is stable. Now we will move to one more example. With that, this chapter will be closed. That is copper. Atomic number of copper is 29 and electronic configuration -2, 2s2, 2p6, 3s2, 3p6, 4s2, if we count the electrons, 10, 20. Now 3d, 9. So this shows the outermost subshell 3d is neither fully filled nor exactly half filled. So copper should be unstable, but it was practically found that copper metal is stable unless it combines with any reagent. So to account for its stability, electronic configuration can be changed slightly like this. From 4s, there are 2 electrons in 4s. We will shift 1 electron to 3d. Then 3d will become completely filled, 4s will become exactly half filled. So it will be like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d. Now, the outermost shell, if we take 4s1 is half filled, 3d is fully filled. Therefore, this electronic configuration, like in the case of 4s1 and 3d5, 4s1 and 3d10 accounts for the stability of copper metal. That's about the relationship between electronic configuration and stability. So always atoms of those elements whose outermost shells are exactly half filled or completely filled are said to be stable. So these are the examples. Right. Now we will see one more example wherein we are not going to shift any electron, but that is stable. This is the last example. That is argon. Atomic number 18. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6. Now this is the outermost shell which is completely filled, and that is equal to 8 electrons which are present in the outermost shell. And arrangement of these electrons or distribution of these electrons in the outermost shell is said to be electronic configuration. So these are means all the electrons, how they are distributed. This is electronic configuration in the outermost shell, and this is equal to octet, which is accountable for its stability because it is completely filled. So this is stable element. So that's about the relationship between electronic configuration and stability of the elements. Thank you, children.